we present a new, fast calibration technique for projector camera systems. This technique allows a fast geometric calibration for projections onto arbitrary surfaces. Our technique is based on a hybrid approach which has two components: an active offline determination of the projector camera correspondences via binary patterns, and a passive online update of the correspondences by evaluating the optical flow. The first projector camera correspondences are determined by projecting a point pattern. Each point of the pattern has a unique ID, which is binary coded. The binary code is projected at the corresponding point position. By finding the point in the camera image, reading the binary coded ID, and restoring the point ID, the projector camera correspondence is calculated. This allows a geometric calibration for a point grid with a resolution of 30 by 30 samples in approximately 2.5 seconds. This time can be nearly halved by combining binary with spatial coding, or by synchronizing the projection with the camera feedback in hardware. Once the system is calibrated, we can display radiometrically compensated images as long as the projector is static. However, if the camera is moved, the geometric calibration between projector and camera is no longer valid, and distortions become perceivable. Here comes the second component of our technique into play, which is based on image analysis. It has the goal to create a camera-to-camera correspondence between the first camera position and the new camera position. This is done via optical flow analysis. The system tries to find features between the two camera images and computes motion vectors. This step is triggered every time the camera stops to move and it has a new position. Since we have only sample features, interpolation and triangulation of values of the motion vectors create a continuous lookup table which contains the movement vectors between corresponding pixels in the two camera images. With the known projector camera correspondence for the first camera position and the movement vectors of the new camera position, it is now possible to compute a geometric, nearly correct image for the new camera position without projecting a calibration pattern. It is also possible to calculate the optical flow of the camera movement in dynamic content. This is done by transforming the grabbed movie frame and comparing it with the corresponding camera image. Our system predicts the quality of this image-based correction and starts the active offline calibration step if the quality becomes too low. Based on this hybrid approach, we can offer rapid calibration for projecting images on nearly every arbitrary surface. The result is the impression of a projection onto a white plane seen from different positions.